All right, so here's what we know so far about attraction trends. We know that valence electrons determine reactivity. That's why they're important to know, and that's why we have to make sure that we know that based on the group something's in, that'll tell you how many valence electrons it has. We know that noble gases are the most stable, right? Those are the Kardashians' level of stability and nobility, and everything wants to sort of dress up like them and have the same electrons as they do. So that would be 8 valence electrons. All of the noble gases have 8 valence electrons. So to be like them, all of the other atoms are trying to get those 8 valence electrons. Stability is the goal. That's why atoms are trying to do this. It is actually not a desire to be like a noble gas. It is that the most stable electron configuration is where every subshell is full, and it turns out the noble gases have those full subshells. So they're trying to be stable like that. So that's why they want to be like noble gases. All right. So as we discussed in class with much fanfare and ado, this is all about attraction. And if you understand that much, you'll be in great shape. And unfortunately, on my iPod, which you'd barely be able to hear anyway, I don't have a good dance song. So you'll just have to imagine Justin Bieber singing it, not Justin Bieber, Justin Timberlake singing at this point. But anyway, all right. So what you see here is a nucleus of females and a bunch of males around as like electrons, so to say. And it's the attraction that makes everything happen here for the trends. So as you look at the periodic table, the increasing desire to keep electrons will increase as you get toward the noble gas, and the one with the least number of electrons, helium in this case, has the most desire to keep its electrons. It has the most to lose. It only has 2, so it's going to be very careful to make sure that it knows where those 2 electrons are at any given time, because if it loses 1 electron, it will no longer be a noble gas, and if it gains 1 electron, it won't be a noble gas. So it's wanting to stay where they are, and the trend to keep electrons increases on this side and decreases on this side, the francium type side. All right, hopefully that makes sense. That seemed to make more sense in class. But here we go. So then we watched Death Fighter. And Death Fighter showed you Boo Boo Jeffries and Scorponok and a bunch of other um, there's a bunch of other fighters in between those two. And Boo Boo Jeffries was the worst. You can see her that her fighting was her weakness, and then group settings as well. And her strengths were her relationship with her mom. So what does all that mean? So electronegativity, what this does is it sort of gives a rating for every element on the periodic table as to how good it is to attract another electron, sort of a bonding electron or an electron that it would have put in front of it. And as you can see here, just like when you're playing those video games, the higher the number, the better you are at this fighting for an additional electron, and the lower the number, the worse you are. And the trend is that it starts at cesium and it gets better and better and better and better, and fluorine is the max. Now, a couple things you'll notice here. These noble gases are not involved, and that's because if you were to put an additional electron in front of a noble gas, it still wouldn't want to do anything because it's a noble gas. It has its 8 valence electrons. It has all its subshells full. And so adding another electron is just going to sort of upset the apple cart. So they don't want any more electrons. So fluorine is the maximum here for electronegativity. And we have Boo Boo Jeffries is sort of down here. These are the atoms that don't want to really fight for another electron. And up here is the Scorponok. That's the biggest, best fighter for electrons. And as you go away, you start, if you remember the video, you'll start getting to certain things like Pyro and Doom Snake. I can't remember his name. But anyway, as you get away from fluorine, you'll have different other various things. So as you can see here, strontium is not as good as titanium, and titanium is not as good as cobalt, and cobalt is not as good as it is better than aluminum, not as good as carbon. Notice here, the other thing actually that we should know for all these trends, hydrogen sort of belongs over here, sort of maybe above boron. I keep saying above carbon, but maybe above boron as I'm looking at this makes more sense as you look at the numbers. So it's slightly better than boron, not quite as good as carbon in electronegativity. But since it's a non-metal, for the periodic trends, hydrogen sort of belongs on this side of things. All right, so ionization energy, if you remember this as the energy required to remove an electron, Now the noble gases are involved, but the same trend it remains in the sense that since things on this end of the periodic table like to hold on to their electrons, it'll take a lot of energy for you to remove an electron from them. They don't want to lose their electrons. They're all very close to, they either are noble gases or close to noble gases, or don't have a bunch of electrons, so they don't want to lose them. So these are very big into holding on to their electrons. And then again, down here in cesium barium area, they are not that big into holding on to electrons. So they have very low, but low comparatively numbers for ionization energy. So you need to remember that ionization energy is the energy required to remove an electron. It'll decrease as you go down a group, and that's because you're adding more rings around, more energy levels around that atom. So you're getting the electrons further and further away. And you're also increasing the number of electrons. So the electrons are less meaningful as you add more and more. And it decreases across a period-ish. As you see, there's not perfect. But it does sort of decrease across the period. If you really want to see why these dips occur, look at the electron configuration of beryllium versus boron, and you'll see beryllium has full subshells and boron doesn't. You'll see nitrogen has half-filled p subshell and oxygen doesn't. So that's the energy gain to having everything going in the same direction. So there is explanations for all that. Nothing I would ever really ask you to know right now. Just know the general trend is cesium toward helium increases. Now, the atomic radius, a lot of people say that's the one that's backward. It's backward in the sense that the biggest is here at cesium and the smallest is here at helium, but it's for the same reason. Helium really loves its electrons. It's going to keep them close. Cesium is less interested in its electrons, so it lets them wander off, and thus the atomic radius, the distance from the center nucleus of an atom all the way to the outermost electron, is going to be large for cesium because it's sort of not caring about that one electron flying around. And as you get closer to helium, which is very interested in keeping its electrons close and tight and nearby, will have the smallest radius. And as you see, radius for radii for noble gases is pretty small compared to the ones next to them. And so the trend here is it'll decrease headed toward helium, or you can say it increases headed toward cesium. But every one as you go down gets bigger, and every one as you go across gets smaller. And to investigate that a little more, oh, there we go, decreasing size going that way. All right, so first of all, the size, if you keep things close and tight, you look here with these sheep are in a small radius because this shepherd is keeping them very close together, making sure he has them all well controlled, something like helium or neon or fluorine would do. However, down here, he's got them all over the place. They're wandering off, and that's why his radius is larger, and that's what cesium would do. It just sort of lets its electrons wander off because it's not as invested in keeping them close to it. All right, so looking at going down a group, if we're looking at this group here, we're looking at lithium, sodium, and potassium, so the increasing size that would happen here. That happens because lithium has just the 2 energy levels. If we sort of look Bohr model-y, right? Sodium has 3 energy levels, and potassium has the 4 energy levels. And that should be clear to you because potassium's in period 4, sodium period 3, lithium period 2. So that's the number of rings around. So because of that, every atom is getting bigger because you've added another ring and all other things are the same. The valence electron is the same. It's only 1 electron in that outermost shell. So the attraction for the nucleus to that outermost shell is similar in each, and because you're adding another energy level each time, that's why it would get bigger as you went from lithium to sodium. So that should make sense. As you go across a period, though, you're not adding another energy level. You're just adding more electrons to that final energy level. And because of that, the attraction of the nucleus for that outer energy level is increasing. When there's only 1 electron out there, this nucleus doesn't have a lot of attraction for that 1 electron. Think of it, if this is your family and your grandparents live next door and your cousins live in the same town, but then you have this one aunt or uncle that lives way out in the middle of nowhere and nobody really wants to go pick him up or see how he's doing because it's such a long drive and it's just him. But if he, if he has a couple other things, other people living with him, now his house becomes more important. There's more people to visit when you go. And if he had a whole 8 people in his house or whatever, then there'd be a lot more people to visit. It's a closer relationship to that nucleus. And if you really think about sort of the one-to-oneness of this proton to electron attraction, these protons in the middle here need that outer shell electrons to actually find an electron to be attracted to. Whereas in this case, most of the protons can find an electron closer to be attracted to. There's only one proton that is looking for that outermost electron. Anyway, and then we talked about the shielding effect. Another reason why this, more so here, right? The reason why this electron can't feel the attraction for the nucleus is a shielding effect. So I tried to put on a wig to remind you that there's attraction going on here, right? The electrons are trying to be attracted to the nucleus. And the problem is these electrons in the lower energy levels are sort of blocking and repelling these electrons from feeling that attraction. So it's harder for outer electrons to feel attraction to the nucleus because inner electrons keep sort of pushing them back and blocking their access to seeing all the nucleus and its beauty. All right. I think that's about all with that, but I'm going to do this real quick, even though this is going to make it more than 10 minutes, because I don't want to do this again. So calcium, if we talk about ionic radius, calcium has 20 protons being attracted, 20 electrons being kept in place by 20 protons here in the center. If we make calcium into its ion, so it has these two outermost electrons here that it will want to lose, so it'll it'll lose those electrons, which allows calcium now to have the outer shell, the valence electrons, the 8 valence electrons of argon. So now it has 18 total electrons, just like argon, but 20 protons dragging those 18 electrons in. And because of that attraction, those electrons are going to be more drawn to that center nucleus, more drawn to that 20 protons, and that'll make it smaller compared to what it was before it lost those 2 electrons. Also, people in class noticed this now has only 3 energy levels, and before it had 4 energy levels. So that's yet another reason why it's going to get smaller. So positive cations, positive ions tend to get smaller because they're losing electrons. They're bringing the remaining electrons in a little bit closer, and they're often losing an energy level, which also makes them a little thinner in the grand scheme of things. Negative anions, things in the upper corner, which are trying to gain electrons because they're so close to noble gas, like chlorine. Chlorine has 7 valence electrons. By picking up an electron, it has 8. That makes chlorine think it's a noble gas, which is happy and stable. However, the problem is now you're trying to get 17 protons to draw the attention of 18 electrons. It's no longer a one-to-one situation. They're outnumbered. And because of that, the attraction is not as strong as it would have been if there were as many or even more protons than electrons. And because of that, this atom radius tends to get a little bigger. And when you consider the fact that also electrons repel each other, that's going to help sort of make that atom spread out a little more because there's not enough attraction to the nucleus to keep them all in place. So in the grand scheme of things, all 3 of these species have 18 electrons: calcium with a 2+ charge, argon, and this chlorine with a minus charge. They all have sort of the argon electron configuration. Calcium has 20 protons to keep everything in check, so they actually come closer to the calcium nucleus than they would versus argon, which only has 18 protons to sort of bring those electrons into the center, versus chlorine, which now only has 17 protons to bring those 18 electrons to the center. All right, hopefully that made sense. If nothing else, it's not the worst video I've made. It's not. All right, have a great day.